We'll begin our study of industrial control systems with a unit on thermometry. And this is the first lecture on thermometry. It's page 1 in your notes. There are 4 industrial temperature scales that are in use. You see them here: Celsius and Kelvin, Fahrenheit and Rankin. And 3 important temperatures on these scales are the boiling point of water, the freezing point of water, and absolute zero. And as you're no doubt aware, absolute zero is a temperature at which molecular motion appears to stop. It's the coldest attainable temperature. So I have on the next page an illustration of how absolute zero can be easily measured in the lab. Now this page is not in your notes, so please just follow along. This is called an absolute zero test apparatus. It's simply a hollow stainless steel ball that's filled with a gas. It's connected by a hollow tube to a pressure gauge. And so the pressure of gas molecules in the ball are registered on the pressure gauge. We can start by immersing the stainless steel ball in a container of liquid. Let's say it's boiling water at 100 degrees Celsius. We would measure a certain pressure. Then we take it out of the boiling water and let's put it in an ice bath, and we'd measure a lower temperature, 0 degrees C, and as you likely know, the pressure of the gas will be lower because the molecules slow down. There are fewer collisions of the gas molecules with the walls of the container per second, and the collisions have less kinetic energy, so they're less forceful. Connect those with a line. And we can do better than that. Let's take the stainless steel ball, we'll immerse it in a container of dry ice. So dry ice is carbon dioxide, solid carbon dioxide, which sublimes at minus 79 degrees Celsius. And if we throw a chunk of dry ice in a liquid that will not freeze at that temperature, such as acetone or methanol, the CO2 sublimes and the temperature will quickly drop to minus 79 Celsius. And we can measure that temperature and we'll record a pressure on the pressure gauge that is lower still. We can do one better than this. Let's take some liquid nitrogen, which boils at minus 196. Let's immerse the stainless steel ball into the liquid nitrogen and we'll measure a very low temperature and a lower pressure still. If we join those 4 points with a straight line and draw a line, extend it to intersect the x-axis, the x-intercept where p is equal to 0, that would be found to be minus 273.15 degrees Celsius. So at that point, there's virtually no pressure registering because the molecules have stopped moving, if you will. Certainly any gas would be condensed to a liquid. Any liquid would be frozen at that temperature, and the molecules of the solid are probably not vibrating very much. Molecular motion is essentially stopped at absolute zero. Having an absolute temperature scale is important in the sciences. There are some calculations that can be done on the Celsius scale, but for some we need an absolute temperature scale. Here's an example just to get you thinking about it. Here's a gas with a temperature of 100 Kelvin. Its volume is 1 liter and will hold pressure and mass constant. As you likely know, if we double the Kelvin temperature, we'll double the volume. If we increase the Kelvin temperature by a factor of 2, we increase the volume by a factor of 2. So at 200 Kelvin, that same gas is now expanded to 2 liters. And this works on the Kelvin scale. But look at the Celsius scale. Let's say our initial temperature is minus 100 degrees Celsius, and the volume is 1 liter. Now we want to double the temperature. Now what happens when you double minus 100? You get minus 200. So instead of getting hotter, the gas is getting colder. And what's the volume? You see, the scale simply doesn't work for many calculations. We need an absolute scale often in the sciences. Let's go back and look at these temperature scales. So you'll note that both the Kelvin scale and the Rankin scale are absolute scales. That is, the coldest possible temperature, absolute zero, is set to 0 on these 2 scales. You'll also want to notice that there are 100 divisions between the freezing point and the boiling point of water on the Celsius scale and on the Kelvin scale, which simply means they have the same sensitivity. A 1 Celsius degree temperature rise is equivalent to 1 Kelvin degree temperature rise. The only difference between the Celsius and Kelvin scale is that all the Kelvin temperatures are 273.2 degrees higher than the Celsius scale. Since we want to make absolute zero on the Celsius scale become zero, we simply add 273.2 to it. And we do that for all Celsius temperatures to convert them to Kelvin. And likewise, you'd subtract 273.2 from all Kelvin temperatures to convert them to Celsius. But take a look at the Fahrenheit scale. Now, owing to our geographic proximity to the states where we're located, you may be familiar with the Fahrenheit scale. The freezing point is 32 and the boiling point is 212. You'll notice that there are in fact 180 divisions between the freezing point and the boiling point of water on the Fahrenheit scale, which simply means that the Fahrenheit scale is a more sensitive scale than the Celsius or Kelvin scale. In fact, it's 1.8 times more sensitive, 180 divisions instead of 100 divisions for the same temperature change. Now, the Rankin scale is to the Fahrenheit scale what the Kelvin scale is to the Celsius scale. It's simply the absolute scale counterpart. So absolute zero on the Fahrenheit scale is minus 459.7. We want that to read zero, so we would simply add 459.7 to all the Fahrenheit temperatures to make them Rankin temperatures. And similarly, we'd subtract 459.7 degrees from all the Rankin temperatures to make them Fahrenheit temperatures. So a 100 Celsius degree temperature change is the same as a 100 Kelvin degree temperature change, and those are equal to 180 Fahrenheit degree temperature change or 180 Rankin degree temperature change. There's an important piece of notation that you want to pick up on here. And let me illustrate with an example. Let's say we want to measure a temperature change, delta T, T2 minus T1. Now, a temperature change can also be called a temperature difference or a temperature differential. These are all the same thing. Let's say that the temperature in the lab is 20 degrees Celsius, but outside is 12 degrees Celsius. So we could say, what's the delta T? What's the temperature differential between these temperatures? Well, we'd say T2 minus T1, 20 degrees C, minus 12 degrees C is, note here please, 8 Celsius degrees, not 8 degrees C. See, when the degree symbol follows the Celsius, that means it's a temperature change. If the degree symbol precedes the Celsius symbol, that means it's a temperature. So 8 degrees Celsius is a temperature, but 8 Celsius degrees is a temperature change. This might seem insignificant, but it's pretty important. When you read a temperature or temperature differential in print, you want to be clear as to what it is you're reading. Is it a temperature? Is it a temperature difference? And so the position of the degree symbol tells us that. So now this might make sense to you. I can say that 100 Kelvin degree temperature change between the freezing point and boiling point of water on the Kelvin scale is equivalent to 100 Celsius degree difference on the Celsius scale, which is equivalent to a 180 Fahrenheit degree temperature change, which is equivalent to 180 Rankin degree temperature change. Or I can write these dividing all terms by 100. I can say a 1 Kelvin degree temperature change is equivalent to a 1 Celsius degree temperature change is equivalent to a 1.8 Fahrenheit degree temperature change or 1.8 Rankin degree temperature change. It happens in calculations that we encounter a temperature differential. For example, the heat capacity of water is 1 calorie per gram Celsius degree. Means it takes 1 calorie of heat to raise 1 gram of water by a temperature change of 1 Celsius degree. And so I know that that now means the same thing as 1 calorie per gram Kelvin degree, because a Kelvin degree temperature change is equivalent to a Celsius degree temperature change. So Celsius degrees are the same as Kelvin degrees, but degrees C does not equal degrees K, right? Degrees C plus 273.2 equals degrees K. So you need to keep those two notations in your mind. If the temperature increases by 5 Celsius degrees, what's the Fahrenheit temperature change? What is the Fahrenheit degree temperature change that's equivalent to a 5 Celsius degree temperature change? Well, we could use our conversion factor, which is right here. There's 1.8 Fahrenheit degrees is equivalent to 1 Celsius degree. So follow the units. I can say 1 Celsius degree is equal to 1.8 Fahrenheit degrees. So 1.8 times 5 is equal to 9 Fahrenheit degree temperature change. So be careful to keep those two distinct in your mind. Now you may be wondering about the use of the degree symbol with Kelvin. You've probably been taught that we don't use degree symbols with Kelvin. I certainly was taught that, but I noticed that many people on the web are using the degree symbol with Kelvin, and I like to use it, and I would encourage you to use it simply because it does help us differentiate between a temperature, as for example degrees Kelvin, versus a temperature change, Kelvin degrees. Without the degree symbol, we really don't know for sure what the unit means, except in the context of the problem. If you go to the next page, I have some graphs plotted. On this first one, I have Celsius, Kelvin, and Rankin plotted on the same graph. These are the values, their values on the y-axis versus Fahrenheit on the x-axis. And the first thing you probably notice is that the Celsius and the Kelvin scale, well, they run completely parallel. That is, their slopes are the same, and that the Kelvin temperatures are simply 273.2 degrees higher than the corresponding Celsius temperatures. You'll also notice the Rankin scale is an absolute scale with the coldest temperature, absolute zero, is at 0, like Kelvin, but the slope of the Rankin temperature is quite a bit greater. In fact, it's 1.8 times greater than that of the Kelvin scale, as we saw. On the next graph, we have Celsius degrees and Kelvin again plotted, but this time we have the Fahrenheit degree, and the x-axis is in degrees Rankin this time. This is interesting. Note that the Fahrenheit temperature scale is a more sensitive scale, and so the slope is greater. Let me point this out to you and see if we can make sense of it. You'll notice that there are 2 points at which the Fahrenheit scale intersects the Celsius scale, and it also intersects the Kelvin scale, which means there's some temperature at which degrees Fahrenheit equals degrees Celsius, and they are the same temperature. The same is true for Fahrenheit and Kelvin. So note here, at temperatures below this point, degrees Fahrenheit reads lower than degrees C, but degrees C is actually colder. Let's take a temperature of, say, minus 200 degrees Fahrenheit. On the Fahrenheit scale, if we drag a line down here from the point of intersection, that's approximately that's approximately, say, 250 degrees Rankin. But if we drop a line down from minus 200 degrees Celsius, that's actually closer to, say, about 140 degrees Rankin. So in fact, minus 200 Celsius is quite a bit colder than minus 200 Fahrenheit. Here's the point where they're equal. Now at any temperature above this point of equality, then a Celsius temperature is actually hotter than the same Fahrenheit temperature. Let's draw a line at, say, plus 200. And we'll drop a line down from plus 200 Fahrenheit, and that reads what? About, let's say, 650 degrees Rankin. But if we drop a line from plus 200 Celsius down to the Rankin scale, that's going to read about 6, 7, 8, let's call it 840 degrees Rankin. So at any temperature above this point of intersection, a temperature on the Celsius scale is actually hotter than the same temperature on the Fahrenheit scale. And that's because the Fahrenheit scale is exaggerated. The slope is greater by a factor of 1.8 times. Now those same arguments can be applied to Fahrenheit and Kelvin temperatures, because Kelvin and Celsius have the same slope, and Fahrenheit slope is greater by a factor of 1.8. So at any temperature below this point of intersection on the Fahrenheit-Kelvin scales, then a Kelvin temperature is actually colder than the same Fahrenheit temperature. Any temperature above this point of intersection, a Kelvin temperature is actually hotter than the same value in a Fahrenheit scale. On page 3, I have another plot. This time we have Rankin and Fahrenheit and Celsius, their values on the y-axis versus Kelvin on the x-axis. And again, it's easy to see that Fahrenheit and Rankin are running parallel to each other. That is, every Rankin temperature is simply 460 degrees greater than the corresponding Fahrenheit temperature. And again, we can see the slope difference, that the Fahrenheit and Rankin scales are more sensitive, more exaggerated by a factor of 1.8 times compared to the Celsius scale. And you can see that the Rankin scale is an absolute scale with its lowest temperature, absolute zero is at 0, whereas Fahrenheit and Celsius are not absolute scales, and so they have absolute zero at negative values. On this final graph, I have Rankin and Fahrenheit running parallel to each other, and here's the Kelvin scale as well. You see that Kelvin and Rankin both have absolute zero at 0, they're absolute temperature scales. You see that Rankin is a more sensitive scale by a factor of 1.8 times compared to Kelvin. And we see there's a point of intersection between the Fahrenheit scale and the Kelvin scale at which the same temperatures are actually the same values. I'm going to ask you to calculate these in just a couple of minutes. Next, I'd like you to be able to derive formulas to convert between various temperature scales. And you'll find this on page 4. So let me read to you this short explanation, then I'll illustrate by example. What you want to do is start from a temperature of 0 on one scale and multiply or divide by a sensitivity factor or correction, then add or subtract an offset to reach the corresponding temperature on the second or desired scale. Then check your formula by converting other non-zero standard temperatures between scales. So let me illustrate. Let's say to start with we wanted to see how to convert between Celsius and Fahrenheit. So we want to start at Celsius and I want to convert to Fahrenheit. So 0 degrees C, I'll just put here degrees C. We start at 0 on the initial scale. We're going to multiply or divide by sensitivity factor. Recall that the Fahrenheit scale is 1.8 times more sensitive than the Celsius scale. So we multiply by a factor of 1.8. So 0 times 1.8 is 0. We want to make that equal 32. We have to add or subtract an offset. In this case, we're going to add 32. That's equal to degrees Fahrenheit. So 0 times 1.8 is 0, plus 32 is degrees Fahrenheit. If you want the reverse formula, that'll be simply rearrange the equation degrees Fahrenheit minus 32 divided by 1.8 equals degrees C. Now I'd like to check this at some non-zero temperature. Let's move up here. Let's say we start at 100 degrees Celsius. What would that be in Fahrenheit as a check for our formula? We'll say it's going to be 100 degrees C times our sensitivity factor 1.8. We're going to a more sensitive scale. That's 180 plus 32 is in fact 212 degrees Fahrenheit. Yeah, it works. Let's try another one. Let's say we'll do a simple one here just to use our formula. Let's say we want to convert between Celsius and Kelvin. Well, we know how to do that, but I want you to understand the formula, how it works. We'll start on a temperature scale, degrees Celsius. We're going to multiply or divide by sensitivity factor, but in this case, sensitivity factor is 1. 100 divisions on the Celsius scale is the same as 100 divisions on the Kelvin scale. I'll put it in here, but it's kind of redundant. So 0 times 1 is 0, and then we have to add or subtract an offset. In order for 0 to become 273, we have to add 273.2, and that'll give us degrees Kelvin, which we kind of already knew. So I would simply write this as degrees C plus 273.2 equals degrees Kelvin. Okay, that was easy, but I wanted you to see the formula. Let's try another one. Let's say you wanted to convert from Celsius to Rankin. We start at 0 on the initial scale, degrees Celsius, multiply or divide by sensitivity factor. Well, in fact, the Rankin scale, like the Fahrenheit scale, is more sensitive than the Celsius scale by a factor of 1.8, so we multiply by 1.8. So 0 times 1.8 is 0. Then we have to add or subtract this offset. So we're going to have to add 491.7, and that will give us temperature in degrees Rankin. If you want the reverse conversion, it would be degrees Rankin minus 491.7 divided by 1.8 would be degrees Celsius. Let's check it out right up here. Let's say we have 100 degrees Celsius times 1.8, that's 180, plus 491.7 is in fact 671.7 degrees Rankin. It works. All right, let's try another simple one down here. Let's go from, say, Rankin to Kelvin. So we start at 0. Notice we could have started here on the Rankin scale. We could have started on the Kelvin scale, but I'm choosing to go from the Rankin to the Kelvin. So it'll be degrees Rankin. And there's a sensitivity factor. Now going from Rankin to Kelvin, we're going to a less sensitive scale by a factor of 1.8. So to be divided by 1.8. And so 0 divided by 1.8 is 0, and we have no offset. So that's it. It's just Rankin divided by 1.8 is degrees Kelvin. And as you likely know, we could reverse this and say Kelvin times 1.8 is degrees Rankin. All right, easy one. Let's try going from, say, Kelvin all the way over to Fahrenheit. So how would you convert from Kelvin all the way to Fahrenheit? Okay, so say degrees Kelvin. What's the sensitivity factor from Kelvin to Fahrenheit? Fahrenheit is more sensitive by a factor of 1.8. So you're going to multiply, not divide, but multiply by a factor of 1.8. 0 times 1.8 is 0. How does 0 become minus 460? We'd have to subtract minus 460, or 459.7 would be equal to degrees Fahrenheit. If you want the reverse conversion, rearrange the formula. Degrees Fahrenheit plus 459.7. and divided by 1.8 is degrees Kelvin. Let's check it out. Starting at Kelvin all the way to Fahrenheit. So we said we got 373.15 Kelvin times 1.8, and then we have this offset of minus 459.7. So what's that give us? 671.7 subtract 459.7, and that's equal to 212 degrees Fahrenheit. So it works. Okay, I think the only one we didn't do was from Rankin to Fahrenheit. It's probably obvious, but let's finish it up in any case. We start at 0 from where we begin with and go to another scale. So I have degrees Rankin times a sensitivity factor, or divided by sensitivity factor. In this case, they have the same sensitivity. 180 divisions on the Fahrenheit scale is the same as 180 on the Rankin scale, so the factor is 1. We can ignore that. 0 to minus 459.7. Just subtract it, and we have, in fact, degrees Fahrenheit. And hence, degrees Fahrenheit plus 459.7 is equal to degrees Rankin. Right? Recall that to make absolute 0 become 0 on the Rankin scale, we added 459 to it. And I believe those are all the conversions that we need. We can convert any temperature to any other temperature. Now there are problems at the end of this chapter where I'm asking you to interconvert these, and I certainly will have one or two questions like this on a test. I appreciate that some calculators will do some of these conversions, and that's fine if you choose to use it, but I will choose the ones that won't be on your calculator, as you'll see. Just fair warning. There's a few questions on page 5 I'd like us to look at. It says calculate the temperatures at which degrees Celsius and degrees Fahrenheit are equal. Calculate the temperatures at which degrees Fahrenheit and degrees Kelvin are equal. Let's just flip back to our graphs for a moment. Recall we talked about the fact that there is a temperature at which Fahrenheit and Celsius are the same, and where Fahrenheit and Kelvin are the same. I'm asking you, can you calculate what those are? So what is the formula that converts between Celsius and Fahrenheit? Recall degrees C times 1.8, because we're going to a more sensitive scale, plus 32 was equal to degrees Fahrenheit. On a test, you'll be given the thermometers with their reference temperatures on it, so you can work these out yourself at any time. Now at some point, these two temperatures are equal. So let's say instead of having two variables, we just have one, because they'll be the same. We'll just call it T. So I have 1.8 T plus 32 is equal to T. 1.8 T minus T is equal to negative 32. 0.8 T is equal to minus 32. And T equals minus 32 divided by 0.8. Turns out that's minus 40 degrees Fahrenheit is equal to minus 40 degrees Celsius. At minus 40, the temperature is the same, whether it's Fahrenheit or Celsius. At any temperature below minus 40, a Celsius temperature is actually colder than a Fahrenheit temperature. At any temperature above minus 40, a Celsius temperature is actually hotter than a Fahrenheit temperature, because the Fahrenheit scale is more exaggerated. All right, how about the same question here? So notice we're also asked to calculate the temperature at which degrees Fahrenheit and degrees Kelvin are equal. Let's go back and look at our graph. Recall there is a temperature, a high temperature at which Fahrenheit and Kelvin have the same value for the same temperature. Remember in our formulas, the conversion between Kelvin and Fahrenheit, to recall that, starting on the Kelvin scale, going to a more sensitive temperature scale, we could say degrees Kelvin times 1.8 to the Fahrenheit scale. The offset is minus 459.7 equals degrees Fahrenheit. So let's put that formula in and calculate the temperature where these are in fact the same temperature. Degrees Kelvin times 1.8 minus 459.7 equals degrees Fahrenheit. Let's just call that T. I'll say that's 1.8 T minus 459.7 equals T. 1.8 T minus T is plus 459.7. 0.8 T is 459.7. T is equal to 459.7 divided by 0.8. So T is equal to 570, I'll just round it, 575 degrees Fahrenheit, which is equal to 575 Kelvin. There's a few more questions here. Let's think about these. Which is colder, 100 Celsius or 100 Fahrenheit? Well, remember that at any temperature above minus 40, Celsius is hotter, and therefore which one's colder? Well, Fahrenheit would be colder. 100 Fahrenheit is colder than 100 Celsius. Recall the boiling point of water is 100 degrees Celsius, but the boiling point of water on the Fahrenheit scale is 212, so this is nowhere near the boiling point of water. It's definitely colder. Which one's warmer? 0 degrees Celsius or 0 degrees Fahrenheit? Any temperature above minus 40, Celsius is hotter. 0 degrees Fahrenheit is way below freezing. Which is colder, 50 degrees C or 50 degrees Fahrenheit? Any temperature greater than minus 40, Celsius is hotter, and therefore Fahrenheit is colder. Which is warmer, minus 30 degrees Celsius or minus 30 degrees Fahrenheit? Any temperature above minus 40, Celsius is hotter. So minus 30 Celsius is hotter than minus 30 Fahrenheit. Which is colder, minus 60 Celsius or minus 60 Fahrenheit? Any temperature below minus 40, Celsius is colder. There's one more method for converting temperatures between scales, and this does not use formulas. You can use reference points on the temperature scales. Provided you're given temperature scales with reference points, and you will be on a test, you should be able to interconvert. So here's how that's done. For example, the first one says convert 22 degrees Fahrenheit to degrees Celsius. Let me illustrate here. So find the reference point that's as close as you can to your temperature. So the temperature is 22 degrees Fahrenheit. What's the closest reference temperature? The closest reference temperature is the freezing point of water at 32. So I can say the difference between 22 and 32 is 10 Fahrenheit degrees temperature difference. Let's convert that to a temperature difference in Celsius. We multiply by a ratio of 1 Celsius degree for every 1.8 Fahrenheit degrees. And that's equal to 5.6. Now where did I get this from? Remember, there's 100 divisions between the freezing point and boiling point of water on the Celsius scale is equivalent to 180 divisions on the Fahrenheit scale. So if you prefer, you could write here 100 Celsius degrees is equivalent to 180 Fahrenheit degrees. These are temperature changes, temperature difference, not temperature. 10 Fahrenheit degrees temperature difference is equivalent to a 5.6 Celsius degrees temperature difference below the freezing point of water. Right? This is below the freezing point of water. So on the Celsius scale, the freezing point is at 0. So what would the temperature be if it's 5.6 Celsius degrees below the freezing point? Be minus 5.6 degrees Celsius. A temperature difference of 5.6 Celsius degrees below 0 is a temperature of minus 5.6. Clever, eh? Wish I'd thought of that. So here it is. 10 Fahrenheit degree temperature change, that is below the freezing point of water, which is 32, times the conversion factor for temperature change, 1 Celsius degree for every 1.8 Fahrenheit degree. The units will cancel. Fahrenheit degrees cancel. We now have units of Celsius degrees. We are 5.6 Celsius degrees below the freezing point. On the Celsius scale, the freezing point is 0, so 5.6 below that is negative 5.6. All right, let's try number 2. We're asked to convert a temperature of 165 degrees Celsius to degrees Fahrenheit without using a formula, by using the method of temperature references. Okay, so where is 165 Celsius? Well, it's somewhere about 65 degrees. This is 65 Celsius degrees above the boiling point. How many Fahrenheit degrees would that be above the boiling point? Well, 65 Celsius degrees, and there are 1.8 Fahrenheit degrees for every 1 Celsius degree. Units again will guide us and cancel. That turns out to be 117 Fahrenheit degrees above the boiling point. The boiling point is 212 degrees Fahrenheit. This then is 329 degrees Fahrenheit is equivalent to 165 degrees Celsius. Here it is. We say 165 Celsius is 65 Celsius degrees above the boiling point of water. 65 Celsius degrees times 1.8 Fahrenheit degree per Celsius degree converts that to a temperature change in Fahrenheit degrees, which is 117 Fahrenheit degrees above the boiling point. Added to the boiling point is 329 Fahrenheit. Number 3 says convert 300 degrees Kelvin to degrees Rankin. Okay, we're going to use the reference method. Let's find 300 Kelvin on the Kelvin scale. That's about here somewhere. Now, how far is that from a reference temperature? Well, we could use a variety. We could use the boiling point, freezing point. I'm going to choose absolute zero because it's just so easy this way. The numbers are simple. So this is 300 Kelvin degrees greater than absolute zero. So I want to know what that is above the absolute zero on the Rankin scale. So I can simply say 300 Kelvin degrees, convert Kelvin degrees to Rankin degrees. Recall, the Rankin scale is 1.8 times more sensitive. So we multiply by 1.8, and we get 540 Rankin degrees above absolute zero. And since absolute zero starts at zero, that'd simply be 540 degrees Rankin is equivalent to a temperature of 300 Kelvin. So 300 Kelvin is 300 Kelvin degrees above absolute zero. 300 Kelvin degrees is equivalent to 540 Rankin degrees above absolute zero. That's 540 degrees Rankin. So at this point, you should be able to do problems 1 through 4 at the end of this unit. And so I'm assigning them to you as homework. Let me point out to you that beginning on page 29, we have problems. There's problems 1 through 4. And the problems continue on page 30 and page 31. And then the answers to the problems are on page 32 and 33. So you should go ahead and get started on those. And that concludes this first lesson on temperature measuring scales.